Jumping up to a constant speed propeller is not an easy task. Today, we're not going to be talking about a governor or flyweights, but instead how to use the levers themselves. Quick disclaimer, please don't use this video as a substitute for professional instruction. Before we consider how our new constant speed propellers work, let's review the fixed pitch variety first. Propellers are the way which engine power is converted into thrust, accelerating air backwards, pushing the airplane forward. How does it do this? Well, propellers are just wing blades on sticks. The lift force of the blade, turned 90 degrees, is the airplane's thrust. This lift can be varied in two ways. If the blades spin faster, they'll produce more lift, resulting in more thrust for the airplane. You're probably familiar with these fixed pitch propellers and their method of control. More throttle means more RPMs, which means more thrust. However, there is a second way to adjust the lift of a wing blade, through its angle of attack. How can we control the blade's angle of attack? Well, on a propeller, it's called its pitch. On modern constant speed propeller applications, this pitch is automatically adjusted by a governor. The governor's job is to govern or maintain the RPM. It does this by balancing the forces trying to spin the propeller, called torques. What's one torque spinning the propeller? The engine, of course. Its job is to use fuel and air to make the propeller spin faster. Conversely, the propeller's wing blades will generate induced drag as they slice through the air. This induced drag slows the propeller down, opposing that engine torque. The governor will only be controlling the blades in order to do its job. For example, if the throttle is opened, the engine will produce more torque. How should the governor react? By increasing pitch to what's known as a coarse pitch. Induced drag increases, and this balances out with the increased engine torque from earlier to maintain that RPM. Now let's try playing with our new lever, the propeller lever, by moving it forward. This requests a higher RPM from the governor, and the pitch will be decreased, decreasing the blade's induced drag, and the blade spin faster. Note that the engine torque remains the same this entire time. As you'd expect, this is called a fine pitch setting. Why do we need a constant speed propeller anyway? Like most things, it's to save fuel. Let's first examine the classic fixed pitch system. We've just reached cruise altitude at top of climb, so let's reduce power for economy. By pulling the throttle back, we constrict the amount of air going into the engine, which reduces how hard the cylinder is pushing and reduces the RPM. However, there's a significant loss of thrust because the propeller is now spinning slower. Seems obvious, I know. But now let's compare this to a constant speed propeller. At top of climb, we'll reduce the propeller lever instead of the throttle. The propeller lever doesn't affect the engine directly, it turns the blades coarser to force that decreased RPM. It's only the connected crankshaft that's causing the engine to slow down. So suppose both a fixed pitch and constant speed propeller were at the same speed. Which propeller has blades at a steeper angle of attack? And which one would generate more thrust? The constant speed one. In general, fuel economy is tied to RPM. By maintaining thrust using the lower speed, the constant speed propellers gain their efficiency advantage. I can't see the propeller's pitch from the cockpit anyway. So how do we know what's going on? Of course, we've got engine gauges for that. You've probably only used the tachometer for engine power before, but with constant speed propellers, we must introduce a new gauge, the manifold pressure. What's a manifold, and why should we care about its pressure? Instead of pressure, let's actually think of it as manifold suction. The manifold refers to the intake manifold, the pipe for intake air, downstream of the throttle plate. What's responsible for creating this flow of air? Well, it's each of the pistons in their intake stroke. If the throttle's opened, the engine would consume all the fuel-air mixture it can, and it would run at full tilt. A throttle restricts the engine. As we close the throttle plate, we start constricting the engine. The manifold pressure decreases from its maximum of 29.92. Why 29.92? Because at full throttle, the restrictions are lifted, so the engine can draw maximum atmospheric pressure. And what's atmospheric pressure at sea level? 29.92 inches of mercury. Each of the manifold pressure and tachometer can't tell you the power individually. Only by looking at them together can we have a sense for what the engine is doing. Let's now put everything we've learned together to actually fly the airplane over the sequence of an entire flight. At takeoff, maximum thrust and power are needed, so the levers are fully forward. Think of low gear on a bicycle. The pedals are spinning fast, but you're not pushing too hard on them. The blades also spin fast, but with small bites of the air. As we gain speed, the propeller blade's relative wind changes, so drag will decrease. The balance between the torques has now been upset. The engine will have the advantage and push the blades to turn faster. What should the governor do? Will automatically turn the blades coarser, preventing an overspeed. Starting from the departure climb, the propeller lever is reduced to the climb power setting. Why? To save fuel, that's all. Sometimes operating procedures call for what's known as 25 squared, or 25 inches of manifold pressure and 2500 RPM. The order here does matter. Throttle, then propeller, then mixture. Hypothetically, let's examine a very high manifold pressure coupled with a very low RPM. There will be too much fuel in the cylinders and allowed too much time to compress, leading to detonation, which, as you may recall, is bad. So remember, left to right reduction or throw the power away. As the climb continues to higher altitude, the manifold pressure will continue dropping. Is our engine losing power? Yes, indeed. The ambient pressure drops the higher we climb, and this limits the amount of air and fuel the engine is able to draw. This is why super and turbochargers exist. They can sometimes boost manifold pressure above 29.92 inches for extra power. For cruise, the power is reduced once more. We'll consult the operating handbook for the most efficient power setting. Back to our bicycle analogy, we're now pedaling slowly and pushing relatively hard on the pedals. The propeller blades are spinning slower too, and taking much larger bites out of the air. At the top of our approach, we'll continue reducing power to intercept the glide slope. Should we use the propeller lever again? Actually, no. We want the propeller lever full fine for two reasons. First, the resultant fine pitch will be useful in event of a missed approach, where full power is needed as quickly as possible. In addition, the propellers will present more surface area into the relative wind to increase drag, speeding up the descent. What if you had to do a missed approach though? Power obviously needs to be increased, and now the opposite direction from before. It's from right to left. Mixture, propeller, throttle, as if you were reining the power back in. This, again, discourages opportunities for detonation to occur. Okay, we've made a great landing with throttle idle and propeller fully forward. When riding a bicycle slowly, you'd rather be in low gear, pedaling a little faster and easier. Similarly, the blades are in fine pitch, and the throttle makes the engine push lightly to generate the little thrust that's needed to taxi. The blades also rest on their fine pitch stops at low RPM. Otherwise, the governor would push the blades all the way to an ultra low pitch and generate zero thrust. The fine pitch stops makes sure the blades continue to take tiny bites out of the air on the ground. During shutdown, the blades are kept at fine pitch too. Fine pitch means less opposing torque, which will make the starter motor's job easier next time we start up. To summarize, the propeller lever can be thought as the gear selector on your bicycle or car. Low gear or fine pitch is for low speeds at takeoff and approach, and high gear or coarse pitch is for cruising at altitude. The constant speed propeller is a complex and powerful tool that pilots like you can use to maximize the engine's capabilities across all phases of flight. Thanks for watching, and good luck in your complex aircraft training.